There is a lake in New Zealand where tourists kayak on summer mornings. The water is still, the mountains around it are beautiful. The town on its edge has cafes, a waterfront, a promenade. People fish from the shore, children swim in it. 4 to 5 miles beneath all of it, the rock is molten, and it has never stopped moving. 1,800 years ago, it moved too much. In a matter of hours, the entire landscape of an island was transformed beyond recognition. The eruption column rose approximately 25 miles into the sky. Pyroclastic flows exploded outward in every direction at up to 560 miles per hour, not channeled down a mountainside, but spreading across flat ground, swallowing valleys, overwhelming ridges, climbing over mountain ranges as if they were not there. An area larger than many countries was buried under more than 100 meters of ash and rock in less time than it takes to cross a city. Then the cloud kept rising. It entered the upper atmosphere and began to travel. The ash reached Antarctica, 3,700 miles away. It left a layer in the polar ice that scientists can still find and measure today. The atmospheric fallout spread across the planet, and on the other side of the world, in civilizations that had no knowledge this place even existed, people began to notice something was wrong with the sky. Ancient Roman historians recorded strange red sunsets and a sun that seemed to be losing its light. Chinese astronomers documented atmospheric phenomena they had no framework to explain. Neither civilization had any way of knowing what had happened, or that the source was a lake that looked from the surface like somewhere you might spend a quiet afternoon. That eruption is the most violent the world has seen in 5,000 years, and it is not the only one this volcano has produced. Everyone knows Yellowstone. Yellowstone has not had a major eruption in 640,000 years. This volcano has erupted 28 to 29 times in just the last 26,000 years. By the only metric that actually measures geological restlessness, this is not Yellowstone's lesser cousin. It is something the world has simply chosen not to look at. In 2022, it reminded the world it was still there. Over 1,800 earthquakes rattled beneath the lake in a single year. The lake bed rose. A magnitude 5.7 earthquake sent a tsunami rolling across the surface toward the town built on the shore above it. The volcano is called Taupo. The lake is called Lake Taupō. The town on its edge is also called Taupo, and today we're going beneath that lake to uncover what it has already done, why its volcanic history is so unusual, and what scientists are finding inside the restless system beneath it. Before we continue, if you enjoy videos like this, kindly give this one a like and subscribe to the channel if you haven't. And if you feel like sharing, let me know in the comments. Where in the world are you watching from today? And what's the time over there? Now let's continue. Words often become familiar long before they become understood. Supervolcano is one of them. It appears in documentaries, headlines, and conversations, carrying an impression of immense danger. Yet the scientific meaning is far more precise. It does not describe a special family of volcanoes. It marks a threshold, a level of eruptive power so great that it stands apart from ordinary volcanic events. According to the United States Geological Survey, the term applies to any volcanic system capable of releasing more than 240 cubic miles of material during a single eruption. That level corresponds to 8 on the Volcanic Explosivity Index, the highest category on the scale. The Volcanic Explosivity Index measures eruptions by the amount of material they eject, and each step upward represents roughly 10 times more erupted volume than the one before it. The eruption of Mount St. Helens in 1980 reached level 5. Krakatoa, whose explosion echoed across the ocean in 1883, reached level 6. Tambora, erupting in 1815 and bringing the year without a summer, reached level 7. A level 8 eruption releases about 10 times more material than Tambora, placing it in a category where comparisons begin to lose their meaning. This difference explains why the landscape around a supervolcano often appears surprisingly ordinary. Many people expect towering peaks with smoking summits shaped over centuries by flowing lava. A supervolcano usually leaves behind something very different. During an eruption of extraordinary size, so much molten rock escapes that the ground above the chamber can no longer support itself. The surface sinks inward, forming an enormous basin known as a caldera. Lakes, forests, and towns may eventually occupy that depression, giving little hint of the event that created it. The material driving these eruptions also behaves differently from the lava many people imagine. Supervolcanoes commonly produce rhyolite magma, a thick mixture rich in silica and packed with dissolved gases. Its dense texture prevents those gases from escaping easily as the magma rises. Pressure builds steadily within the chamber until the surrounding rock can no longer contain it. When that balance finally breaks, the release comes with explosive force, sending shattered rock, volcanic ash, and scorching gases high into the atmosphere instead of allowing molten rock to spread across the ground in broad rivers. Only a few dozen volcanic systems on Earth meet this extraordinary standard. Current scientific estimates suggest somewhere between 20 and 40 exist across the planet, though researchers continue refining that number as new evidence emerges. Yellowstone has become the most widely recognized example, largely through decades of public attention and scientific study. Topo belongs in that same rare group, yet it occupies a different place within it. Among known rhyolite calderas, it has remained exceptionally active through recent geological history. That distinction reshapes the story entirely, because about 25,700 years ago, this remarkable system demonstrated the full measure of its power, permanently transforming the landscape that would one day become New Zealand's largest lake. Geologists often speak of time with a perspective unlike any calendar. Within that immense span, 25,700 years feels remarkably recent, a moment still close enough for the planet to remember in extraordinary detail. That was when the Oruanui eruption unfolded, the most recent supereruption known on Earth. Entire generations of landscapes have appeared since then, yet in geological history, the event remains almost within reach, preserved in rock layers, lake sediments, and distant ice. The volume released during those days stretches beyond ordinary imagination. Scientists estimate that about 280 cubic miles of volcanic material burst from the system. Spread evenly, that amount could blanket the entire state of Texas beneath roughly 7 feet of ash and shattered rock. Cities, rivers, forests, plains, and every familiar landmark would disappear beneath the same layer. The comparison offers only a glimpse, since no single landscape can truly capture the scale of an eruption that reshaped an entire region in such a short span. Historical eruptions provide useful reference points, though each comparison reveals an even greater difference. Tambora erupted in 1815, releasing enough material to alter weather patterns around the world and contribute to the year without a summer. Harvests failed across Europe and North America, and many thousands of lives were lost through famine and disease. Oruanui expelled more than 7 times that volume. Krakatoa, whose explosion in 1883 echoed across oceans and remains one of history's most famous volcanic disasters, released only a small fraction by comparison. Oruanui exceeded it by more than 100 times. The eruption itself unfolded through at least 10 separate phases over several days, perhaps extending into weeks. Its earliest moments were driven by violent encounters between rising magma and underground water. Each collision flashed water into steam with explosive force, fragmenting rock into enormous clouds of ash. As groundwater became less influential, towering eruption columns climbed higher into the atmosphere, sustained by tremendous heat and relentless pressure rising from the chamber below. Across New Zealand's North Island, fast moving pyroclastic density currents transformed everything in their path. These turbulent mixtures of scorching gas, volcanic ash, and shattered stone raced outward until familiar valleys, ridges, and forests ceased to exist in recognizable form. Close to the source, deposits hardened into ignimbrite layers, reaching nearly 660 feet thick. Earlier landscapes disappeared beneath entirely new foundations, leaving future rivers and forests to develop upon freshly created ground. While immense quantities of magma escaped, the enormous chamber supporting the surface steadily emptied. Eventually, the overlying rock could no longer support its own weight. It fractured and dropped inward, forming a broad caldera about 14 miles across. Rainfall and flowing water gradually filled that depression over thousands of years. The broad blue surface, now known as Lake Taupō, rests within that collapsed basin, preserving the outline of one of Earth's greatest volcanic events. Evidence of the eruption extends far beyond New Zealand itself. Ash settled across the Chatham Islands, almost 385 miles from the source, leaving a layer several inches thick. Geologists recognize this deposit as the Kawakawa tephra, one of the southern hemisphere's most valuable chronological markers. Wherever that distinctive layer appears in sediments, it records the same unforgettable point in Earth's history, 25,700 years ago. Some volcanic eruptions shape the ground around them. Others reach far beyond the horizon, entering a part of the atmosphere where weather can no longer pull them back to Earth within a few days. Oruanui belonged to that second kind. Its towering eruption column climbed into the stratosphere, a high atmospheric layer where tiny particles may remain suspended for years, carried by broad air currents that circle much of the planet before finally settling. Along with volcanic ash came an immense release of sulfur dioxide. Researchers estimate that roughly 260 teragrams entered the stratosphere during the eruption. Once there, the gas gradually reacted with water vapor, producing countless droplets known as sulfate aerosols. These pale particles reflected part of the sun's incoming energy back into space. Less sunlight reached the surface below, allowing temperatures to decline over broad regions, while the aerosol cloud remained aloft. Evidence of this atmospheric journey still survives in one of Earth's greatest natural archives. At the South Pole, snow accumulated year after year, trapping traces of volcanic material inside growing layers of ice. One of the most detailed records comes from the West Antarctic Ice Sheet Divide ice core, where scientists identified an exceptionally large sulfate deposit linked to Oruanui. The measured concentration approaches 500 kilograms for every square mile represented within that frozen record, making it one of the strongest volcanic sulfate signals preserved during roughly 60,000 years of accumulated ice. Climate researchers also examine the event through a measure known as radiative forcing, which describes how strongly something changes Earth's energy balance. Estimates suggest the Oruanui aerosol cloud produced a cooling influence of roughly negative 13 watts for every square yard of the planet's surface. For comparison, the eruption of Pinatubo in 1991 generated approximately -3 watts and cooled global temperatures for more than a year. Oruanui's estimated atmospheric effect was therefore more than 4 times greater, illustrating how extraordinary the eruption appeared within climate models. Even so, the story has become more nuanced as new evidence continues to emerge. Research published during 2023 examined sediments collected from an old basin near Auckland and arrived at an intriguing conclusion. The geological record does not fully match earlier expectations of prolonged worldwide cooling. Scientists now propose that the southern hemisphere location of the eruption may have limited how efficiently aerosols spread between hemispheres. The eruption clearly altered climate, yet the exact scale and duration remain active subjects of investigation, reminding researchers that Earth's atmosphere often behaves with greater complexity than models alone can predict. Across New Zealand, the ecological consequences unfolded on a different scale. A surprisingly thin layer of volcanic ash can strip leaves from forests for many months, interrupting growth and reshaping habitats. Oruanui buried much of the North Island beneath deposits measured in many feet instead of inches. Forests vanished, waterways shifted, and the range of the giant flightless moa changed dramatically as ecosystems adjusted to transformed landscapes. No human community witnessed these changes. New Zealand remained unoccupied, leaving plants and animals as the only living participants in the eruption's immediate aftermath. Over thousands of years, fresh forests spread across the volcanic deposits, rivers carved new valleys through them, and life gradually returned to terrain built from the remains of one of Earth's greatest eruptions. Time left another signature within the forests that once covered the Taupō region. Deep beneath layers of volcanic deposits, a stand of trees at Puriora remained preserved after the eruption ended their growth forever. Their annual rings became an extraordinary calendar. By matching those patterns with carefully calibrated radiocarbon records, scientists narrowed the event to late summer or early autumn, around 232 of the Common Era. Few eruptions from so long ago carry a date established with such remarkable confidence. This eruption is known as the Hatepe eruption, or simply the Taupō eruption. It belongs to level 7 on the Volcanic Explosivity Index, placing it among the greatest eruptions of the recent geological past. Although it released far less material than the earlier Oruanui supereruption, researchers recognize it for something different. It is widely regarded as the most violent volcanic eruption on Earth during the last 5,000 years. That distinction comes from the extraordinary speed at which magma escaped, the immense energy released, and the behavior of the devastating volcanic currents that followed. Scientists estimate that roughly 8 cubic miles of magma emerged during the eruption. As expanding gases shattered that magma into ash, pumice, and fragmented rock, the total volume of erupted material grew to about 25 cubic miles. The final ignimbrite alone accounted for nearly 7 cubic miles of scorching debris. These figures reveal that the eruption was not merely powerful. It converted molten rock into an immense, moving landscape of airborne fragments and ground-sweeping deposits within an astonishingly brief span of time. The eruption unfolded through several recognizable stages instead of one uninterrupted explosion. Geologists identify these episodes as separate phases, labeled from the first through the sixth within the preserved record. During the earliest activity, rising magma encountered lake water near the Horomatangi Reef area. Water changed instantly into expanding steam, driving violent explosions that blasted ash and pumice skyward. Each stage settled into a distinct layer around the basin, creating a sequence that remains visible in cliffs and exposed outcrops surrounding Lake Taupo today. Those layers serve as a detailed archive, allowing researchers to reconstruct the eruption almost page by page. Measured by erupted ash, the Hatepe eruption exceeded Tambora by roughly twofold. Tambora transformed weather patterns across much of the world during 1815 and became one of history's defining volcanic disasters. Hatepe surpassed it in ash production while generating an eruption column that climbed even farther into the atmosphere. Rising about 31 miles above Earth's surface, the column reached well into the stratosphere, where fine particles could travel immense distances before gradually returning to the ground. Commercial aircraft operate far below that height, making the eruption column a towering feature unlike anything encountered in ordinary flight. For a time, the atmosphere carried the finest fragments upward while heavier material continued falling across the surrounding land. The immense column depended upon a constant upward surge of heat and volcanic gases. Eventually, that support weakened. Gravity reclaimed the towering plume, and its upper reaches began folding back toward the landscape that had produced them. Within those descending masses, the eruption entered a different chapter, one driven less by height than by astonishing motion across the surface of the Earth. Gravity eventually reclaimed the towering eruption column. After rising high above the landscape, the immense cloud could no longer support its own weight. Instead of continuing upward, countless tons of volcanic ash, shattered pumice, rock fragments, and intensely heated gases collapsed toward the surface. The descending mass spread outward in every direction, forming a pyroclastic density current, one of the fastest and most destructive natural processes known. During the Hatepe eruption, this current reached an intensity that still stands among the greatest ever reconstructed from geological evidence. Researchers estimate that the leading edge traveled between roughly 370 and 560 miles per hour. At its greatest speed, it moved faster than the cruising speed of many commercial aircraft. Within fewer than 15 minutes, the current swept across approximately 7,700 square miles of New Zealand's North Island. Such distances normally belong to journeys measured over hours of driving or days of walking. Here they disappeared almost instantly beneath a moving blanket of heat and volcanic debris. Temperature added another extraordinary dimension to its power. Portions of the current approached about 932 degrees Fahrenheit. At such heat, leaves ignited almost immediately, wood charred within moments, and living tissue could not endure exposure. Trees, birds, insects, and even microscopic organisms within the upper soil vanished wherever the hottest parts of the current passed. The landscape did not experience ordinary burning. It underwent an abrupt transformation driven by extreme heat combined with astonishing velocity. The current behaved unlike a conventional landslide or avalanche. As it accelerated, compressed air collected beneath its base, forming a thin cushion that greatly reduced friction against the ground. This process allowed the dense volcanic mixture to glide with surprising efficiency instead of grinding slowly across the surface. Scientists describe this as a highly fluidized flow, one capable of spreading almost like a liquid while still carrying enormous quantities of solid material. That unusual motion explains why the deposits appear so remarkably even across large areas today. Perhaps the most astonishing consequence of this movement appeared where mountains stood in its path. Ordinary flows follow valleys and descend slopes under the pull of gravity. The Hatepe current climbed instead of stopping. It swept over the Tongariro volcanic region and crossed the Kaimanawa Mountains, surging more than 4,900 feet uphill before descending the opposite side. Geological evidence preserves this remarkable journey within continuous ignimbrite deposits, demonstrating that the current possessed enough momentum to overtop major barriers instead of being diverted around them. Comparison with more familiar eruptions reveals the extraordinary scale of this event. The lateral blast from Mount St. Helens during 1980 devastated roughly 230 square miles and reached speeds estimated near 300 miles per hour. The Hatepe pyroclastic current spread across an area more than 30 times larger while attaining even greater velocity. Though both eruptions remain important chapters in volcanic history, they occupy very different levels of energy and geographic reach. As the current crossed valleys and ridges alike, it reshaped the land itself. In some places, it deposited thick sheets of ignimbrite. Elsewhere, its tremendous force stripped away older ground before leaving fresh volcanic material behind. Hills softened, depressions filled, and countless natural features disappeared beneath a newly formed surface. Once the last waves settled and ash drifted through the air, the altered landscape surrounded a lake whose own response became part of the same remarkable geological story. Volcanic eruptions do not always finish when the ash settles. Sometimes their greatest influence continues through water, unfolding across years instead of hours. After the Hatepe eruption reshaped the Taupō Basin, enormous quantities of pumice, ash, and volcanic debris accumulated around the lake's natural outlet. The channel that normally carried water into the Waikato River became blocked. Rain continued to fall, streams continued to enter the basin, yet the lake could no longer drain as it once had. A natural dam, built by the eruption itself, gradually transformed the balance of the landscape. Year after year, the trapped water climbed higher. Geological evidence indicates that Lake Taupō eventually stood about 115 feet above its present level. The broad basin became an immense reservoir held back by loose volcanic deposits rather than solid bedrock. Every passing season added more weight against that barrier. The surface appeared calm, yet the pressure pressing against the blockage increased continuously as the lake stored an ever greater volume of water behind it. No natural dam built from freshly erupted material lasts forever. Water slowly found weak points within the volcanic barrier, seeping through small openings and enlarging them grain by grain. As erosion accelerated, the structure lost its strength until a catastrophic breach occurred. More than 4 cubic miles of water rushed into the Waikato drainage system. That astonishing volume is roughly equal to 8 million Olympic swimming pools emptying within the same event, releasing an inland sea that had been waiting for decades behind the temporary obstruction. The flood that followed bore little resemblance to the modern Waikato River. Scientists estimate that peak discharge approached about 1 million cubic feet of water every second. Today, the river carries only a tiny fraction of that amount. For more than a week, the flood surged at roughly 200 times the present flow, racing across the valley with enough force to strip banks, shift enormous boulders, and reorganize entire stretches of the river system. The event became one of the largest known freshwater floods in New Zealand's geological history. As the torrent spread downstream, it carved fresh channels through older sediments while abandoning others that had guided the river before. Great beds of rounded stone accumulated along the valley floor, where they remain visible to geologists studying the aftermath. Entire forests disappeared beneath thick layers of flood deposits. Their trunks, roots, and buried soils survived within the sediment, creating remarkable natural records that still reveal the character of landscapes growing nearly 1800 years before the present. Among the most enduring consequences was a permanent alteration to the Waikato River itself. Before the Hatepe eruption, the river drained toward the Hauraki Gulf. The tremendous flood reorganized that drainage pattern, cutting a new route westward across the Hamilton lowlands until the river ultimately reached the Tasman Sea. New Zealand's longest river continues to follow that path today, tracing a course established by a volcanic flood that lasted only days, yet permanently redirected the movement of water across an entire region. The flood gradually subsided, though its signature never disappeared. Geologists can trace its deposits for well over 125 miles downstream. Even today, rounded fragments of pale pumice carried by that ancient event continue washing onto beaches along New Zealand's North Island, drifting through rivers and waves as enduring travelers from an eruption that reshaped both land and water. Light can preserve the memory of an eruption long after ash has settled beyond the horizon. Once the Hatepe eruption column climbed nearly 31 miles into the stratosphere, its finest particles entered an atmospheric pathway very different from ordinary weather. Rain clouds and storms no longer controlled their movement. Sulfate aerosols drifted within high-altitude circulation, where they could remain suspended for many months while spreading across enormous distances before gradually returning to Earth's surface. Among the written records surviving from the ancient world are descriptions of skies that no longer behaved as expected. One account comes from the Roman historian Herodian, who described unusual atmospheric conditions during the period associated by some researchers with the Hatepe eruption. He wrote of discolored skies and sunlight that appeared diminished or strangely tinted. These observations have attracted scientific interest because volcanic aerosols, suspended high above the weather, can scatter sunlight, changing both its brightness and its color in ways that observers often remember with remarkable clarity. Far away, another collection of historical writings preserves similar observations. Fan Ye, compiling the annals of the Eastern Han dynasty, recorded unusual appearances in the heavens together with disrupted weather during roughly the same era. Red skies and other atmospheric irregularities entered the historical record without any understanding of their possible origin. The chroniclers described what careful observers witnessed above them, leaving later generations to compare those accounts with geological evidence gathered thousands of miles away. Neither civilization possessed any knowledge of New Zealand. To scholars in Rome and Imperial China, the South Pacific, beyond familiar trade routes, remained outside the known world. No messenger could have arrived carrying news of an eruption from a distant island they had never imagined. Their records, therefore, stand as independent observations of unusual skies rather than reports connected to a known volcanic disaster. They documented changing light without recognizing that the source might have risen from the opposite side of the planet. Even so, the connection remains an active scientific discussion rather than an established conclusion. The historical observations themselves are genuine. The uncertainty lies in the eruption's exact date. Some interpretations of ancient accounts suggest an eruption around 186 of the Common Era, while detailed radiocarbon analysis from the buried Purora forest points instead toward approximately 232 of the Common Era. Because those dates do not perfectly align, researchers continue evaluating whether the Roman and Chinese descriptions truly reflect the Hatepe eruption or another atmospheric event whose evidence has yet to be fully understood. Comparisons with more recent history provide valuable perspective. Tambora released about half the ash produced by Hatepe during its eruption in 1815. Its atmospheric effects contributed to harvest failures and widespread hardship during the following year across parts of Europe and North America. Given Hatepe's greater eruption column and larger volume of volcanic material, scientists conclude that its atmospheric influence was at least comparable and may have been even more extensive, though the precise consequences remain difficult to reconstruct after so many centuries. The eruption also disturbed the atmosphere in another remarkable way. As the towering column collapsed, it generated immense pressure waves that traveled outward through the air. Scientific estimates suggest the sound may have carried for roughly 3,100 miles, potentially reaching Australia, Papua New Guinea, Indonesia, and islands scattered across the Pacific Ocean. Voices recorded unusual skies far away. Distant listeners may have heard an unfamiliar rumble, yet no human stood close enough to witness the eruption itself. History usually survives through voices. Someone watches the horizon, records an unfamiliar sky, or tells a story that passes from one generation to the next. The Hatepe eruption left none of those human traces. When it transformed the heart of New Zealand's North Island, no people lived there. The first Polynesian voyagers, whose descendants became the Maori, would not arrive until roughly 1,000 years later. One of the greatest volcanic events of the last 5,000 years unfolded across a landscape without a single human observer. That absence shaped the way the eruption entered history. There are no eyewitness accounts describing the first explosions, no songs recalling falling ash, and no inherited memories carried through families. Nothing survives from human experience because there was no human experience to preserve. Every detail known today comes from the earth itself. Rocks preserve layers of ash. Lake sediments record changing conditions. Ice, far away, captures volcanic particles carried through the atmosphere. Buried forests retain the final moments of living trees. The planet became both the witness and the archive. Among those natural records, the Purora buried forest holds a special place. Trees that once stood across the landscape were overwhelmed during the eruption and sealed beneath volcanic deposits. In several locations, their trunks still emerge from the ground where erosion has exposed them again after many centuries. Growth rings inside those trees formed a precise chronological sequence. By comparing those patterns with carefully calibrated radiocarbon records, scientists established the eruption's age with remarkable confidence. The forest did not survive the catastrophe, yet in its preserved wood it carried forward the date of the event more faithfully than any written document could have done. Although nobody stood close enough to witness the eruption, people living far across the Pacific may have sensed that something extraordinary had happened. The collapse of the towering eruption column generated immense atmospheric pressure waves capable of traveling roughly 3,100 miles. Communities on distant islands may have heard an unfamiliar rumble arriving from beyond the horizon. Without knowledge of New Zealand or the volcanic source, there would have been no way to connect that distant sound to an eruption unfolding across the ocean. If oral traditions ever preserved those memories, no surviving record can confidently link them to Hatepe. The ecological consequences unfolded without human interruption. Across roughly 7,700 square miles, the hottest pyroclastic currents destroyed forests, birds, insects, freshwater life, and countless smaller organisms that formed the foundation of local ecosystems. Rivers changed, soils were buried beneath volcanic deposits, and familiar habitats disappeared. Recovery depended entirely upon natural processes. Wind carried seeds, surviving plants slowly spread into devastated ground. Animals gradually returned from surrounding regions as the environment became capable of supporting life once more. There is a distinctive quality to an event that unfolds beyond human awareness. Unlike famous disasters remembered through eyewitness testimony, the Hatepe eruption belongs almost entirely to geological time. The Earth released extraordinary energy according to processes that neither required nor acknowledged human presence. Many centuries later, Polynesian navigators reached these islands and established enduring communities. They built homes, cultivated the land, and developed traditions upon ground created by forces they never witnessed, yet whose legacy remained woven through the landscape beneath their feet. When people finally reached the shores of Lake Taupō, the land had already lived through chapters beyond human memory. Polynesian navigators arrived in New Zealand around 1280 of the Common Era, nearly 1,000 years after the Hatepe eruption transformed the heart of the North Island. They stepped into a landscape that appeared settled, yet its valleys, lake basin, and volcanic peaks still carried the imprint of immense geological change. Warm springs, steaming ground, and volcanic mountains revealed that the forces shaping the region had not disappeared. They continued as part of everyday life. Living upon volcanic terrain demanded careful adaptation. Across much of the central North Island, soils formed from pumice and volcanic ash contained low amounts of cobalt and several other trace elements needed for healthy plant growth. Agriculture proved more difficult than in many coastal regions. The people who became known as Ngati Tuaredoa developed a way of life suited to these conditions. Lake Taupō provided abundant fish, surrounding forests offered birds and edible plants, and knowledge of seasonal resources became deeply woven into community life. Through generations of changing alliances and conflict, they remained one of the region's enduring powers. The lake itself received a name celebrating place rather than danger. Its full Maori name, Taupo Nui Atia, is commonly translated as the Great Cloak of Tia, honoring the ancestral explorer associated with discovering the lake. The broad blue water stretching among volcanic mountains inspired a name rooted in memory and identity. The enormous volcanic system concealed beneath the surface required no separate acknowledgement. It revealed its presence through the landscape itself, where warm water emerged naturally and the ground occasionally reminded its inhabitants that deeper processes continued below. Within Maori tradition, one of the lake's most significant guardians is Horomatangi, a taniwha dwelling in the depths. Taniwha occupy many roles within Maori knowledge, sometimes protecting places, sometimes warning of danger, and sometimes expressing the power of natural forces. The name Horomatangi also belongs to the reef near the center of Lake Taupō, recognized today as the most volcanically active part of the modern system. There, heated water rises through hydrothermal vents from beneath the lake bed, linking traditional knowledge with a location that remains scientifically important. Another enduring tradition tells of Ngator Wairangi, the high priest who climbed Mount Tongariro and faced deadly cold upon its slopes. Calling to Hawaii, the ancestral homeland, he sought sacred fire to preserve his life. According to the story, that fire traveled beneath the land, emerging first at White Island, then through Rotorua, before reaching Tongariro itself. Modern geological mapping shows that these places align closely with the Taupo volcanic zone, where heat continues moving upward through Earth's crust. The narrative follows a pathway remarkably similar to the distribution of volcanic activity recognized today. The surrounding mountains also became living participants within Maori cosmology. Tongariro, Ruapehu, Taranaki, and Pihanga were remembered as powerful beings whose struggles filled the land with fire, smoke, and trembling ground. Their final resting places explain the arrangement of volcanic peaks across the North Island, while preserving an understanding that these mountains possessed energy, motion, and influence extending beyond ordinary stone. These traditions did not describe magma chambers, tectonic plates, or hydrothermal systems in scientific language. They expressed careful observation through genealogy, story, and sacred history. The lake's guardian, the underground journey of fire, and the living mountains all reflected generations spent listening to a landscape that continued changing long after the great eruptions had passed. Beneath those stories, the volcanic system itself remained active, following rhythms measured not in lifetimes, but across hundreds of thousands of years. Every great volcanic landscape begins with motion too gradual for human senses to notice. Far below New Zealand's North Island, enormous slabs of Earth's outer shell continue shifting without pause, advancing only tiny distances each year. Those movements seem insignificant within a single lifetime, yet over hundreds of thousands of years they build one of the planet's most productive volcanic regions. Lake Taupō exists because these deep motions have never truly ceased. Roughly 4 to 5 miles beneath the island, the Pacific Plate descends beneath the Australian Plate along the Hikurangi subduction zone. The Pacific Plate sinks into the mantle at a pace of about 3/4 of an inch each year. That rate appears almost motionless when measured from one season to the next, though the movement never stops. As the descending plate travels deeper into Earth's interior, increasing temperature and pressure begin changing both the minerals within the rock and the fluids trapped inside them. Those fluids play a crucial role in creating magma. Water and other volatile compounds escape from the descending plate into the hotter rocks above. Their arrival lowers the melting point of those rocks, allowing portions of the mantle to melt without reaching temperatures that would otherwise be required. Newly formed magma becomes less dense than the surrounding material and begins rising toward the surface. This process has repeated for countless ages, continually renewing the volcanic system beneath the central North Island. Another geological process strengthens the system even further. While one plate sinks beneath another, the crust above experiences stretching, known as back arc extension. Instead of remaining compressed, the overlying rocks gradually pull apart. Fractures develop, existing faults widen, and fresh pathways appear through the crust. Rising magma encounters fewer obstacles during its ascent, allowing large volumes to accumulate comparatively close to the surface. The remarkable productivity of the Taupō volcanic zone comes from the partnership between subduction below and crustal stretching above, each process reinforcing the other. Lake Taupō occupies a position directly above this active geological engine. Current evidence indicates that much of its eruptible magma resides roughly 4 to 5 miles beneath the lake floor. By comparison, Yellowstone's principal magma reservoir lies noticeably deeper. A shorter distance between molten rock and the surface allows pressure changes to influence the upper crust more directly. When conditions align for an eruption, magma has less rock to cross before reaching open air, contributing to the rapid style for which Taupō is known. Modern seismic imaging has revealed more about this hidden reservoir than ever before. A study published during 2021 identified at least 60 cubic miles of eruptible melt beneath Lake Taupō. Researchers emphasize that this represents a confirmed minimum rather than a complete measurement. Imaging methods cannot yet resolve every portion of the system with perfect detail, leaving open the possibility that additional molten material remains beyond the present limits of observation. The magma itself also shapes the character of the volcano. Taupō produces rhyolite, a magma rich in silica and abundant dissolved gases. Its thick consistency resists easy escape of those gases, allowing pressure to accumulate over long periods. Sometimes that pressure releases through comparatively modest volcanic activity. At other times, it escapes with extraordinary speed. Across the broader Taupō volcanic zone, geothermal fields continue releasing immense quantities of heat, much of it harnessed today for electrical power. The same engine that warms those waters continues operating beneath the landscape, following rhythms that have endured for hundreds of thousands of years. Modern volcanoes reveal themselves through instruments long before they produce lava or ash. Deep beneath Lake Taupō, networks of sensitive sensors listen continuously for tiny movements within the crust. Each earthquake, each shift of the ground, and each subtle change in elevation becomes another sentence in a conversation between the volcano and the scientists watching it. Most of the time, those signals remain modest, though every so often they gather into patterns that deserve closer attention. During 2019, monitoring stations operated by New Zealand's National Volcanic and Earthquake Monitoring Program recorded more than 1,100 earthquakes within the Taupō caldera. In an ordinary year, only a few hundred such events are expected. Activity began increasing during late April and continued through the following months before reaching its strongest point with a magnitude 5.2 earthquake in early September. It became the largest earthquake detected beneath the lake in several decades, drawing renewed scientific attention to a volcanic system that had remained active beneath the surface all along. Researchers examined this remarkable sequence in detail. A peer-reviewed study published during 2021 concluded that the earthquake swarm originated from volcanic processes rather than ordinary tectonic fault movement alone. The evidence pointed toward fresh magma entering the deeper reservoir, increasing pressure within the volcanic system and producing the observed seismic activity. The study suggested that Taupō was experiencing renewed recharge, a process expected within an active volcanic region even when no eruption follows. Another period of unrest began during May of 2022. Over the months that followed, more than 1,800 earthquakes occurred beneath the lake. Scientists responded by raising the volcanic alert level to level 1, the first time that this had happened since the monitoring system began operating. The decision did not indicate that an eruption was imminent. Instead, it acknowledged that the volcano had entered a state of measurable unrest beyond its usual background behavior, supported by multiple lines of scientific observation. The ground itself confirmed that change was occurring. Satellite positioning instruments installed near Oruanui Reef detected steady uplift across much of the unrest period, measuring roughly 2 1/3 inches each year. An independent survey completed during September of 2022 confirmed that the lake floor had risen by nearly 1 inch since February. Such movement reflects changes occurring far below the surface as magma and heated fluids alter pressure within the crust. Though small in everyday terms, these measurements become highly significant when interpreted alongside earthquake activity. During November of the same year, a magnitude 5.7 earthquake occurred about 5½ miles beneath the lake. The shaking was felt widely across the surrounding region. It also generated a small tsunami within Lake Taupō itself, sending water onto several shorelines and reaching about 130 feet inland at Warawaka Point. Instruments near Oruanui Reef recorded nearly 10 inches of horizontal movement toward the southeast, the greatest displacement ever measured at that location since continuous monitoring began. Viewed across roughly 150 years, these events form part of a longer pattern. Scientists recognize 17 earlier episodes of volcanic unrest beneath Taupo, none of which ended in eruption. Each episode reflects a system adjusting to changes in pressure, heat, and magma movement deep below the landscape. The unrest gradually eased, the alert level returned to normal, and daily life resumed around the lake. Modern instruments can describe how the volcano behaves today, while the geological record reminds us that its story continues across timescales far longer than any single human lifetime. Few volcanoes have become as familiar to the public imagination as Yellowstone. Set within a celebrated national park in the United States, it has inspired decades of documentaries, scientific reports, novels, and disaster films. Millions of visitors walk across its geyser basins each year, while researchers continuously measure earthquakes, ground movement, and geothermal activity. Its last caldera-forming supereruption occurred about 640,000 years ago, while its most recent significant volcanic event, a large rhyolite lava flow, took place roughly 70,000 years ago. Those immense spans of time encourage the impression of a system resting between rare episodes of extraordinary activity. Taupo presents a different story. During the 1995 United States Geological Survey comparison of the Taupo volcanic zone and Yellowstone, researchers concluded that the two systems share many important characteristics. Both have generated enormous volumes of rhyolite magma. Both have persisted across long geological intervals. Both release remarkable quantities of geothermal heat, and both rank among Earth's most significant silicic volcanic provinces. Their similarities explain why scientists often compare them, yet the differences reveal why the comparison cannot end there. The most important distinction lies in how often each volcanic system becomes active. Yellowstone has produced 3 caldera-forming supereruptions during approximately 2,100,000 years. Taupo generated its Great Oruanui supereruption within the past 300,000 years, then continued erupting repeatedly afterward. Geological evidence identifies at least 28 additional eruptions during roughly the last 25,700 years alone. That record reflects a volcano operating on a far more frequent schedule. Instead of storing magma for extraordinarily long intervals between major events, Taupo repeatedly opens pathways that allow pressure to escape through eruptions of varying size. Reservoir size alone does not determine volcanic behavior. Yellowstone contains a substantially larger magma system, with an upper reservoir estimated at roughly 960 cubic miles, while deeper molten material may occupy an even greater volume. Current seismic imaging beneath Lake Taupō confirms at least about 60 cubic miles of eruptible melt. Although considerably smaller, that figure represents only the presently resolvable minimum. More importantly, a smaller reservoir, capable of recharging and erupting comparatively, often cannot be judged less hazardous merely because its capacity is lower. Frequency and style matter alongside total volume. The contrasting geological settings explain much of this difference. Yellowstone sits above a continental hotspot surrounded by relatively thick and stable crust. Taupo occupies an active subduction environment where the Pacific Plate descends beneath the Australian Plate, while the overlying crust continues stretching through back arc extension. Fractures remain plentiful. Fresh magma is supplied continuously from below, and pathways toward the surface develop more readily. Those structural conditions encourage repeated volcanic activity rather than exceptionally prolonged periods of storage. Human geography also changes the comparison. Much of Yellowstone's immediate caldera region remains protected wilderness with relatively sparse permanent settlement. Around Lake Taupō, communities live within the volcanic district itself, and millions of people occupy New Zealand's North Island beyond it. Roads, farms, towns, power stations, and transportation networks all depend upon a landscape created by continuing volcanic processes. Comparing Taupo with Yellowstone, therefore, means more than matching the dimensions of two famous calderas. It requires recognizing that two outwardly similar volcanic systems operate according to different geological rhythms, beneath very different human landscapes, with consequences shaped as much by frequency and location as by the size of the magma reservoir itself. Scientific models allow researchers to explore events that have not yet occurred without turning them into predictions. The scenario that follows comes from published impact studies prepared by GNS Science, together with New Zealand Emergency Management Research. It does not describe what scientists expect tomorrow, next year, or within any particular lifetime. Instead, it examines the consequences of repeating an eruption comparable to the Hatepe event using the best geological evidence and modern hazard modeling available today. The first hours would transform the central North Island with extraordinary speed. Pyroclastic currents could spread across roughly 7,700 square miles while moving at speeds approaching 560 miles each hour. Communities close to the lake would have very little time to respond once such currents formed. Anyone remaining within approximately 50 miles of the caldera after a rapidly escalating eruption would face overwhelming danger. Even with modern communication systems, evacuation would become exceptionally difficult if warning signs accelerated over only a short period. Far beyond the immediate devastation, volcanic ash would reshape daily life across the country. Thick deposits would blanket the North Island, loading rooftops with heavy material, contaminating reservoirs and rivers used for drinking water, damaging crops, and blocking major transportation routes. Ash would also reach the South Island, while prevailing winds could carry measurable quantities toward eastern Australia. The fertile Waikato Basin, one of New Zealand's most important agricultural regions and the center of its dairy industry, could remain unsuitable for productive farming for many years, with recovery depending upon rainfall, soil restoration, and the thickness of volcanic deposits. Waterways would undergo equally profound change. Rivers draining the volcanic region would receive enormous quantities of ash, pumice, and fragmented rock. Lahars, dense mixtures of water and volcanic debris, would surge along existing channels, following valleys for hundreds of miles. These fast-moving flows could destroy bridges, bury farmland beneath thick sediment, alter river courses, and continue long after the eruption itself had ended, as rainfall repeatedly remobilized loose volcanic material left across the landscape. The atmosphere would extend the eruption's influence far beyond New Zealand. An eruption column rising about 25 miles into the stratosphere would disperse ash across major international air routes. Aviation authorities would likely suspend or reroute flights over large areas of the South Pacific for weeks or even months. The much smaller eruption of Eyjafjallajökull in Iceland during 2010 disrupted more than 100,000 flights across Europe within only 6 days. A Hatepe-scale eruption would produce consequences on an entirely different level because of its far greater volume and higher eruption column. Climate models indicate that sulfate aerosols released into the stratosphere would likely reduce temperatures across much of the southern hemisphere for 1 to 2 years, while smaller effects could extend into the northern hemisphere. Growing seasons would shift, agricultural production could decline in several regions, and food supplies would experience additional pressure created by altered weather patterns. The town of Taupo itself offers perhaps the clearest reminder of this geological reality. Around 35,000 people live along the northern shore of the caldera. Waterfront paths, cafes, schools, neighborhoods, and holiday parks stand beside one of Earth's most consequential volcanic systems. They are not facing unusual danger during ordinary days. Their community exists, however, upon the rim of a volcano, whose history reminds scientists why careful monitoring remains an essential companion to everyday life. Forecasting a volcanic eruption is unlike predicting tomorrow's weather or the path of a hurricane. Volcanoes spend much of their existence changing in places no instrument can observe directly. Scientists measure earthquakes, ground movement, volcanic gases, and heat escaping from the surface, then assemble those separate clues into a picture of processes unfolding miles below. That picture grows sharper every year, yet important pieces remain beyond reach, especially when the volcano belongs to the rare class capable of producing supereruptions. Taupo presents an unusually demanding challenge because its eruptions vary enormously in size. Across its history, the volcano has produced comparatively modest lava dome eruptions, as well as events powerful enough to reshape the landscape of an entire country. Current research has not identified a unique sequence of warning signs that clearly separates these very different outcomes during their earliest stages. Earthquake swarms, uplift, and magma movement may appear before both small and much larger eruptions. The paths sometimes resemble one another until comparatively late in the process, leaving uncertainty during the period when decisions matter most. Recent studies of large volcanic systems have also changed scientific thinking about how eruptible magma develops. Earlier models often envisioned reservoirs accumulating gradually across many thousands of years before a major eruption became possible. New evidence suggests that substantial volumes of eruptible magma may assemble over decades or centuries instead. Research at Long Valley Caldera in California indicates that, under certain conditions, the final transition toward a supereruption could occur within as little as about 1 year. That possibility has encouraged scientists to reconsider how rapidly volcanic systems may evolve after long intervals of relative stability. Taupo adds another layer of complexity. During roughly the past 150 years, the volcano has experienced 17 recognized episodes of unrest. None progressed into an eruption. Earthquakes increased, portions of the ground shifted, and volcanic processes became more active before gradually settling again. Because these episodes repeatedly end without an eruption, unrest itself cannot be treated as proof that one is imminent. Every new sequence forces scientists to ask the same careful question. Does this represent another ordinary adjustment within the volcanic system, or the beginning of something more significant? Present knowledge cannot answer that distinction with dependable certainty. Modern monitoring remains extraordinarily valuable despite these limitations. Scientists can identify whether earthquake swarms arise from volcanic activity or ordinary tectonic fault movement. They can detect changes in deformation, follow trends through time, and determine whether unrest is strengthening or fading. What monitoring cannot presently provide is a reliable forecast of the eventual size of an eruption. The earliest signals preceding a small lava dome and those preceding a much larger event may overlap enough that meaningful separation becomes difficult until later stages. Another challenge comes from the age of the monitoring record itself. Continuous satellite positioning measurements at Horomatangi Reef extend back only to the early years of this decade. Improvements to the seismic network following the unrest of 2019 greatly increased the ability to detect smaller earthquakes beneath the lake. Scientists are still establishing what constitutes ordinary, long-term behavior within a volcanic system whose natural rhythms unfold across centuries rather than decades. Current estimates place the annual probability of any eruption at Taupo, regardless of size, at less than 1/10 of 1%. That figure remains very small for any individual year, though it is not zero. Scientific honesty accepts both parts of that statement, recognizing the limits of present forecasting while continuing to improve the observations that make future understanding possible. Every hillside surrounding Lake Taupō holds a memory. Those memories are not preserved in writing or carved into stone by human hands. They exist as layers of ash, pumice, and welded volcanic rock, each deposited during a different eruption, each resting above or below another in an orderly sequence. Volcanologists approach these layers much as historians approach old manuscripts, examining every boundary, every grain, and every chemical signature to reconstruct events separated by thousands of years. This geological archive has allowed scientists to assemble one of the most complete eruption histories for any volcano on Earth. Each deposit represents a moment preserved exactly where it settled. Thick sheets of ignimbrite reveal the passage of scorching pyroclastic currents. Blankets of fine ash trace the direction of ancient winds. Coarser pumice records explosive phases when gas-rich magma fragmented into countless floating fragments. Together, these deposits provide direct physical evidence that can be measured repeatedly by different research teams using independent methods. One of the most valuable techniques in this work is tephrochronology, the science of using volcanic ash layers as chronological markers. Certain eruptions produce ash with a unique chemical composition that distinguishes it from every other volcanic event. The Kawakawa tephra, created during the Oruanui eruption, has become one of the finest reference layers across the South Pacific. Whenever researchers recover sediment from lakes, wetlands, or the ocean floor and encounter this unmistakable ash, they immediately recognize material deposited about 25,700 years ago. A single layer becomes a reliable point in time, shared across an enormous region. The age of the Hatepe eruption reached remarkable precision through another approach. At the buried forest near Purora, trees overwhelmed during the eruption remained preserved where they had grown. Scientists collected 25 consecutive annual growth rings from these trunks and analyzed their changing radiocarbon content. Each ring formed during a known sequence of years, allowing researchers to compare the pattern against an established calibration curve. This process, called radiocarbon wiggle matching, narrowed the eruption date to within about a decade, an extraordinary level of accuracy for an event nearly 2,000 years old. Evidence from Antarctica provides another independent record. Ice accumulating year after year traps tiny quantities of sulfate produced by major volcanic eruptions. The Oruanui eruption left one of the strongest sulfate signals found within approximately 60,000 years of Antarctic ice core history. Researchers compare the timing preserved in those frozen layers with dates established from volcanic deposits in New Zealand. The agreement between these entirely separate archives strengthens confidence that the chronology accurately reflects the sequence of ancient events. Estimating eruption volume requires equally careful work. Scientists measure the thickness of ash and ignimbrite at hundreds of locations, including exposed rock faces, drilled cores, riverbanks, and lake sediments. Those measurements are combined with detailed maps showing how deposits thin with distance from the source. Mathematical models then reconstruct the original volume before erosion and weathering altered the landscape. The enormous estimate for the Oruanui eruption emerged through decades of field observations rather than any single discovery. Many of these records remain visible today. Cliffs surrounding Lake Taupō expose stacked bands of ash, pumice, and ignimbrite that preserve successive eruptions in chronological order. Researchers continue studying these natural cross-sections, while travelers passing along the lakeshore often stand within sight of the same evidence. The archive remains open, adding fresh understanding while preserving a volcanic history written directly into the landscape itself. A single eruption rarely tells the full story of a volcano. The true character of a volcanic system emerges only after thousands of years of observation, when each event is placed beside the next until a pattern begins to appear. Around Lake Taupō, that pattern stretches across nearly 26,000 years, preserved in rock with remarkable clarity. It reveals a volcano that has never remained inactive for long on geological timescales, even after producing one of the greatest eruptions of the recent Earth. Since the Oruanui supereruption about 25,700 years ago, Taupo has erupted at least 28 additional times. Averaged across that immense span, one eruption occurred roughly every 900 years. The intervals, however, were never regular. Some eruptions followed only a few centuries after the previous event, while others were separated by several thousand years. The record resembles a changing rhythm instead of a steady pulse, reminding researchers that volcanic systems follow physical processes rather than predictable calendars. This sustained activity sets Taupo apart from every other known rhyolite caldera of comparable scale. Many large volcanic systems experience exceptionally long dormant intervals after their greatest eruptions. Taupo continued producing fresh eruptions throughout the post-glacial period, maintaining a frequency unmatched among supervolcanoes. Its history demonstrates that enormous caldera-forming events do not necessarily mark the conclusion of volcanic activity. In Taupo's case, they became one chapter within a much longer sequence that continued reshaping the landscape again and again. The eruptions themselves differed dramatically in size and style. Some produced comparatively small rhyolite lava domes that slowly emerged before cooling into solid rock. Others generated towering eruption columns and widespread ash fall. One notable event, known as Unit Saint, occurred around 1460 before the Common Era and reached a volcanic explosivity comparable to the eruption of Mount Pinatubo during 1991. Although far smaller than Oruanui or Hatepe, it remained an exceptionally powerful eruption capable of transforming the surrounding region. Another important chapter appears in the deposits left by the Waimea eruption approximately 3,300 years ago. Archaeologists studying sediments beneath its ash discovered evidence connected with early human activity in the New Zealand region. The volcanic deposit sealed that surface in place, preserving valuable clues about the timing of human presence. In this instance, the geological record and the archaeological record supported one another, demonstrating how volcanic events sometimes become chronological markers for understanding human history as well as natural history. Every eruption added another layer to the landscape, Along sections of the lakeshore, cliffs reveal stacked bands of ash, pumice, and ignimbrite arranged in chronological order. Each band represents a distinct event with its own chemical fingerprint, thickness, and distribution. Field geologists often compare these exposures to pages within a carefully organized volume, where every layer contributes another paragraph to the volcano's biography. Reading them requires patience, measurement, and repeated observation, yet together they preserve an exceptionally complete account of Taupo's changing behavior. Running through this entire sequence is another important discovery. The magma reservoir has not steadily emptied over time. Fresh magma has continued entering the system from greater depths, replenishing material released during earlier eruptions. Modern seismic studies, including the analysis following the unrest of 2019, confirm that this process continues today. Across nearly 26,000 years, Taupo has remained an active volcanic system, sustained by a source that continues renewing itself beneath the landscape. The legacy of a great eruption does not end when ash settles or lava cools. It continues through landscapes that people cross every day without realizing how long their story has been unfolding. Around Lake Taupō, the evidence is woven into beaches, rivers, forests, soils, and warm water rising from the depths. None of these features belong only to the past. Each remains part of an active landscape shaped by volcanic events whose influence still reaches into ordinary life. Along many beaches of New Zealand's North Island, pale fragments of rounded pumice collect among the waves. They are light enough to float and smooth enough to resemble weathered shells, yet they began as violently fragmented magma. Much of this material traces its origin to the Hatepe eruption and the immense flood that followed, which swept volcanic debris into the Waikato River system. For about 1,800 years, rivers have continued carrying, sorting, and redistributing these fragments. Every fresh storm and changing current moves another small portion of that ancient eruption across the landscape. The Waikato River itself tells an even larger geological story. Today, it is the longest river in New Zealand, flowing through farmland, towns, hydroelectric developments, and broad valleys before reaching the sea. Its modern course exists because the Hatepe eruption dramatically altered the region. After volcanic deposits temporarily blocked drainage, the eventual collapse released a tremendous flood that carved the channel followed by the river today. Roads, bridges, farms, and communities now occupy a landscape whose shape was determined by that single volcanic event nearly 2,000 years ago. The ground supporting much of central New Zealand also carries this inheritance. Weather gradually transformed thick accumulations of pumice and volcanic ash into distinctive soils across the volcanic plateau. These deposits provide the foundation for forests and pasture, yet they demand careful management. Their loose texture makes them especially vulnerable to gully erosion during heavy rainfall. They naturally contain low amounts of several trace elements essential for healthy livestock, including cobalt, requiring farmers to supplement grazing animals. Even the grass growing across these fields reflects chemical conditions established by eruptions many centuries before agriculture reached the region. Lake Taupō itself offers another reminder that volcanic processes continue beneath the surface. Swimmers, boaters, and kayakers occasionally encounter patches of water noticeably warmer than the surrounding lake. These warmer areas do not arise from changing sunlight alone. Heat travels upward through hydrothermal vents embedded within the lake floor, where groundwater circulates through hot volcanic rocks before returning to the surface. During the 1998 survey conducted with the research submersible Jago, scientists directly observed hot water emerging near Horomatangi Reef, confirming an active hydrothermal system linked to the deeper volcanic engine. Around portions of the shoreline, steam escapes through cracks in the ground, warm springs emerge naturally, and saturated soils release heat into the air. These features have attracted visitors for generations, yet they also represent visible expressions of ongoing geothermal circulation. Researchers observe them carefully because changes in temperature, chemistry, or discharge may provide valuable information about conditions within the volcanic system. The Purora Buried Forest preserves another remarkable connection between present and past. Tree trunks overwhelmed during the Hatepe eruption still stand where they were engulfed, protected beneath volcanic deposits that halted decay. Visitors can walk among these preserved remains today, encountering a landscape where one moment from nearly 1800 years ago continues almost exactly as it was left. Across beaches, rivers, farmland, forests, and the lake itself, Taupo remains present not as a memory, but as a living influence that continues shaping the world around it. Morning arrives over Lake Taupō with fishing boats leaving the marina, runners following the waterfront paths, and cafes preparing for another day beside the water. Families launch kayaks, anglers search for trout, and travelers gather for skydives, scenic cruises, or the drive toward nearby geothermal attractions. The setting feels welcoming and familiar, shaped by everyday routines rather than reminders of distant geological events. For the people who live here, the lake is woven into ordinary life, providing recreation, livelihoods, and a sense of place. The town of Taupo is home to about 35,000 residents and ranks among New Zealand's most popular inland destinations. Visitors arrive throughout the year to enjoy water sports, trout fishing, lakeside restaurants, hiking, skydiving, and bungee jumping above the Waikato Gorge. Across approximately 238 square miles of blue water, volcanic peaks rise along the horizon, creating one of the country's most recognizable landscapes. The lake appears timeless, inviting people toward its shoreline without revealing the extraordinary process that created it. Everything built around the northern edge of the lake occupies ground formed through repeated volcanic activity. Main streets, neighborhoods, schools, holiday parks, hotels, and lakeside businesses stand upon layers of ash, pumice, and ignimbrite deposited during eruptions spanning roughly 300,000 years. The foundations supporting modern buildings were assembled gradually by successive volcanic episodes, each leaving material that weathered into the terrain supporting today's community. The relationship between town and volcano is therefore direct, although it often remains unnoticed during daily life. One location illustrates this relationship especially well. Horomatangi Reef, recognized as the most volcanically active feature within the present system, lies beneath the lake's surface and serves as a recreational dive site. Divers regularly descend through clear water to explore submerged rock formations and aquatic life without requiring specialized scientific equipment. During the 1998 expedition, using the research submersible Jago, investigators confirmed hydrothermal vents releasing heated water from this same area. A place valued for exploration and recreation also marks one of the principal expressions of the active volcanic system below. Each year, Lake Taupō welcomes approximately 1,300,000 visitors. Most arrive because of its scenery, outdoor activities, or nearby geothermal attractions. Many spend days on the water without realizing they are crossing the flooded center of a giant caldera. Swimming, sailing, paddleboarding, and fishing become ordinary experiences within a landscape whose geological significance is rarely the first thought in anyone's mind. The volcano remains present, though it rarely announces itself beyond the features already woven into the environment. New Zealand maintains one of the world's most advanced volcanic monitoring programs. GeoNet continuously publishes information about earthquakes, ground deformation, volcanic alert levels, and ongoing scientific observations. Emergency management agencies regularly update response plans and communicate hazards using well established procedures. These systems exist because volcanic activity is an enduring part of the country's natural setting, while the probability of any eruption during a single year remains very low. Daily routines continue with understandable confidence, supported by careful observation rather than constant concern. Communities across Earth have long accepted landscapes shaped by natural hazards. Cities occupy floodplains, neighborhoods spread across earthquake faults, and villages flourish beside active volcanoes because those places also offer fertile ground, valuable resources, beauty, and opportunity. Taupo represents one of the clearest expressions of that enduring balance. People have built homes beside an extraordinary lake, embracing its remarkable setting while trusting the careful work of science to watch over the forces that remain active far below its waters. Attention follows familiar paths. Some landscapes become permanent fixtures in documentaries, news reports, and popular imagination, while others remain known mainly to specialists and the communities that live nearby. Volcanic systems are no exception. Their visibility often depends as much upon geography, language, and culture as upon the processes unfolding beneath the ground. Taupo illustrates this pattern with unusual clarity, occupying a central place in volcanology while remaining comparatively unfamiliar to much of the wider world. Yellowstone has become the defining image of the modern supervolcano. Television programs revisit it regularly, disaster films imagine catastrophic eruptions, and news stories return whenever earthquakes or geothermal changes attract public interest. Taupo receives far less international attention despite a record that differs in significant ways. Its eruption history has remained active through the past approximately 1800 years, whereas Yellowstone's last eruption occurred about 70,000 years ago. Among volcanologists, Taupo commands deep respect. Beyond scientific circles in New Zealand, its name appears far less often in public conversation. Part of this difference reflects where each volcano is located. Yellowstone lies within the continental United States, a nation with an exceptionally large scientific community, extensive research institutions, and one of the world's largest English-language media networks. Scientific discoveries made there are rapidly communicated through books, documentaries, educational programs, and international news organizations. Hazards within the United States naturally receive broad coverage because so many global media outlets already maintain strong connections to the country. This pattern is neither surprising nor unusual. It reflects the way information commonly spreads across established cultural and communication networks. Many of Earth's most important volcanic systems occupy a different position. Numerous major calderas and volcanic arcs lie within the southern hemisphere or in nations whose scientific achievements receive less international attention despite their quality. Their research often remains highly respected within earth science while attracting comparatively modest public awareness elsewhere. Taupo belongs to this group. It is among the best monitored volcanic systems on Earth. Yet many people outside New Zealand encounter its name only rarely, if at all. Visibility influences more than public curiosity. Understanding volcanic hazards encourages long term investment in monitoring equipment, infrastructure planning, emergency exercises, and communication systems capable of reaching communities quickly during periods of unrest. Public interest also shapes political support for scientific research and sustained funding across many decades. When a hazard remains largely absent from international discussion, maintaining awareness becomes a continuing responsibility carried by researchers, local authorities, and the people who live alongside the landscape itself. Communicating a risk like Taupo presents an especially difficult challenge. The probability of an eruption during any single year remains very low. The volcano does not dominate the skyline as a towering cone because much of the system lies beneath a broad lake. Its activity unfolds through earthquakes, subtle ground movement, and hydrothermal changes that rarely attract immediate attention outside scientific observation. Explaining why these gradual signals deserve careful study requires patience, consistency, and trust built over many years. There is a quiet irony within this story. The most frequently active rhyolite caldera known on Earth, the site of the planet's most recent supereruption, and the source of the largest eruption during the past 5,000 years, is often recognized first for trout fishing, boating, and beautiful lakeside scenery. Geological history remains unchanged, regardless of how often it enters headlines. The rocks surrounding Lake Taupō continue preserving the same record, offering the same evidence, and reminding careful observers that the distribution of attention has never determined the distribution of natural processes. Numbers often seem reassuring because they appear exact. A percentage fits neatly onto a chart, a report, or a scientific paper, giving the impression that nature has been reduced to something orderly and predictable. Volcanologists know the reality is more nuanced. A probability describes likelihood across many possible futures. It does not identify the particular year when an eruption will begin, nor does it count down toward an appointed date. It offers a statistical view of uncertainty expressed with careful restraint. Current scientific assessments place the annual probability of any eruption at Taupo, regardless of size, at less than 1/10 of 1%. Expressed another way, that represents fewer than one chance in 1,000 during any individual year. Standing alone, such a figure appears remarkably small. A person could spend an entire lifetime beside the lake without witnessing an eruption. Many generations have done exactly that, building communities while the volcano remained in one of its long intervals between eruptive episodes. Probability changes character when viewed across longer spans. A chance repeated year after year gradually accumulates. Over approximately 500 years, an annual probability below 1/10 of 1% produces a cumulative probability approaching 40%. Extend the horizon to about 1,000 years, and the cumulative probability approaches 63%. Continue across geological time, and the likelihood steadily approaches certainty. This is one reason volcanologists think in centuries and millennia instead of individual calendars. The question shifts from whether an eruption is possible to how natural processes unfold across very long intervals. The geological record provides additional perspective. Since the Oruanui supereruption, Taupo has erupted approximately once every 900 years on average, although the intervals have varied substantially. The present pause has lasted about 1,800 years, making it the longest interval recognized within the post-Oruanui sequence. That observation does not imply the volcano is overdue. Magma does not accumulate according to a clock, and volcanic systems do not maintain regular schedules. The average describes past behavior without determining the timing of the next event. Human society measures time differently. Buildings are commonly designed with service lives of roughly 50 years. Emergency plans undergo revision every few years as populations grow and infrastructure changes. Governments develop policies within election cycles, while cities often preserve written histories extending back only centuries. These practical frameworks serve everyday needs exceptionally well, yet they are not naturally aligned with hazards whose recurrence spans many human lifetimes and whose largest eruptions may develop without an unmistakable early signature. Preparing for such events, therefore, becomes a difficult exercise in long-term stewardship. Resources must be invested today for situations that may never arise within the careers of those making the decisions. Public attention naturally gravitates toward immediate concerns whose effects are already visible. Maintaining monitoring networks, refining hazard maps, and supporting continued scientific research require sustained commitment despite the absence of dramatic daily reminders. This challenge extends far beyond Taupo and appears wherever societies confront natural processes operating on timescales much longer than individual experience. The annual probability assigned to Taupo is neither comforting nor alarming. It is a careful summary of present scientific understanding, shaped by observation, measurement, and the geological archive assembled across decades of research. Nature follows physical laws instead of human expectations, allowing intervals to lengthen or shorten without regard for calendars. The landscape surrounding Lake Taupō continues existing within that enduring rhythm, carrying forward a history measured not by generations alone, but by the patient passage of centuries. History often separates civilizations into distinct chapters, each marked by different languages, beliefs, and technologies. Geological time ignores those divisions. The volcanic system beneath Lake Taupō has persisted through every change in human society, continuing its own rhythm, while empires expanded, kingdoms dissolved, and new cultures emerged. Each generation inherited the same landscape, though each understood it through a different lens. When the Hatepe eruption unfolded around 232 after the Common Era, the Roman Empire was passing through one of the most turbulent periods in its history. Political instability, military conflict, economic strain, and competing rulers weakened institutions that had once appeared enduring. Contemporary writers described unusual atmospheric conditions, recording dimmed sunlight and altered skies in distant regions. They possessed no knowledge of an island nation far across the oceans, and no scientific framework capable of connecting those observations to an eruption nearly 7,000 miles away. Across Asia, the Eastern Han Dynasty approached its own conclusion. Court rivalries, regional fragmentation, famine, and rebellion reshaped one of the world's great civilizations. Chinese astronomers maintained careful records of celestial and atmospheric phenomena because they believed the heavens reflected events unfolding on Earth. Some observations from this period describe unusual conditions in the sky, preserving valuable historical information without revealing its source. The immense eruption that contributed volcanic material to the atmosphere remained entirely beyond the geographic horizon of those who documented its effects. Many centuries later, Polynesian navigators reached New Zealand after remarkable voyages across the Pacific Ocean. They encountered a landscape already transformed by eruptions that had ended long before their arrival. Rivers followed channels established by volcanic floods. Pumice covered portions of the terrain, while geothermal activity continued around the lake and surrounding valleys. Communities adapted to these conditions, developing traditions that reflected close observation of the natural world. The lake itself received the name Taupo, expressing beauty and significance within Maori culture. Throughout generations of settlement, no major eruption interrupted that relationship. They lived within the interval, separating one volcanic chapter from the next. European settlers arrived during the 1840s, carrying the developing knowledge of 19th century geology. Their understanding of volcanoes exceeded that of earlier societies, yet the concept of a supervolcano had not emerged. Farms expanded across the volcanic plateau, roads linked growing settlements, wetlands were drained, and towns developed beside the Waikato River. Communities prospered along a watercourse whose modern path had been carved by the tremendous flood released after the Hatepe eruption many centuries earlier. The volcanic origin of that geography remained largely unrecognized during those early decades of settlement. Modern New Zealand occupies a different position than any previous society connected with Taupo. Scientists continuously monitor earthquakes, ground movement, lake behavior, and geothermal activity, using sophisticated instruments unimaginable to earlier civilizations. Emergency planning, hazard assessment, and long-term geological research all contribute to understanding the volcano with increasing precision. At the same time, approximately 3,800,000 people live across New Zealand's North Island, while agriculture, transportation, energy production, and communities depend upon landscapes shaped by earlier eruptions. Public officials must weigh geological risks unfolding across centuries against immediate responsibilities affecting everyday life. Every civilization connected with Taupo has shared one experience despite their profound differences. Each lived during an interval between eruptions. Knowledge changed from mythology to geology, from observation to satellite measurements, yet the volcanic system remained the same. The landscape welcomed generations who interpreted it according to the understanding available in their own time, while the geological record continued preserving the evidence of every completed interval with unwavering patience. Stone remembers with unusual patience. Long after forests have changed, rivers have shifted, and generations have passed from memory, volcanic deposits remain where they fell, preserving a sequence that can still be read. Around Lake Taupō, those layers extend through roughly 300,000 years, forming an uninterrupted archive of activity. Within that record, one pattern appears again and again. Every interval of volcanic rest has eventually given way to another eruption. There is no chapter in which the system permanently ceased. Each caldera became the setting for whatever followed, and every apparent ending proved to be another beginning in geological time. Modern research has added another line to that long history. Seismic investigations, published during 2019, found evidence that fresh magma continues entering the reservoir from greater depths. Measurements of ground movement, reported during 2022, showed portions of the caldera rising and falling as pressure changed within the system. These observations do not describe a volcano fading into inactivity. They reveal one that continues exchanging heat, magma, and fluids through processes that have operated across immense spans of time. The reservoir has not been emptied by earlier eruptions. It continues receiving new material from below. From these observations, volcanologists reach a conclusion that is both careful and remarkably direct. They cannot identify the year of the next eruption. They cannot say whether it will begin within 100 years, 500 years, or 1,000 years. Present science does not provide that level of precision. At the same time, The geological evidence, accumulated across 300,000 years, points toward another certainty. Taupo will erupt again. That conclusion rests upon repeated observation preserved in the landscape itself, not upon speculation or dramatic prediction. The form of that future eruption remains unknown. It may begin as a modest rhyolite dome emerging through part of the lake floor, producing only localized changes at the surface. Another possibility resembles eruptions of intermediate size already preserved within the caldera's history. Across much longer timescales extending well beyond ordinary human planning, the geological archive also includes events comparable to Hatepe and, farther back, the immense Oruanui supereruption. Every one of these outcomes belongs to Taupo's documented past. Existing monitoring systems cannot yet determine which path the next eruption will follow until the volcanic processes themselves begin revealing that answer. Whatever eventually occurs will become part of Earth's enduring archive. Ash carried through the atmosphere will settle into lakes, wetlands, and the ocean, forming a recognizable layer preserved within future sediments. Chemical traces may appear in polar ice, while volcanic minerals become reference points for researchers studying distant environments. Long after landscapes change once again, that deposit will remain available for interpretation, adding another page to the planetary record that future observers will examine with the same care applied to older eruptions today. At this moment, Lake Taupō stretches across approximately 238 square miles of water, reaching a maximum depth of about 610 feet. Beneath the lake floor, roughly 4 to 5 miles below the surface, lies a reservoir containing at least 250 cubic miles of molten rock. Trout travel through cool currents, while warmer water rises where geothermal circulation reaches the lake. Morning and evening cast different colors across the surface, yet the underlying geology remains unchanged. Beauty and geological power exist together here without contradiction, each forming part of the same enduring landscape. Human experience unfolds within remarkably short horizons. Our instincts develop to notice changing weather, approaching danger, the passing of seasons, and the span of a lifetime. Even the longest family histories cover only a handful of generations. Geological time exists far beyond those familiar boundaries, stretching across intervals so immense that ordinary intuition struggles to grasp them. Taupo belongs to that larger rhythm, operating according to processes that neither accelerate nor pause to match human expectations. This difference shapes the way volcanic hazards are understood. A recurrence interval averaging about 900 years already exceeds the lifespan of nearly every institution ever created. The approximately 300,000 years preserved within the volcanic record surrounding Lake Taupō extend still farther, representing hundreds of such intervals layered together. Human memory cannot directly contain a sequence of that length. Instead, understanding emerges through rocks, minerals, sediments, and careful observation, allowing science to reconstruct events no person could have witnessed across a single continuous tradition. The language used to classify volcanoes also reflects this challenge. Terms such as active, dormant, and extinct seem straightforward until they are measured against geological timescales. By ordinary human standards, a volcano that has remained without eruption for approximately 1,800 years appears inactive. Geological evidence tells a different story. Taupo continues producing earthquakes, measurable ground deformation, hydrothermal circulation, and fresh magma entering the reservoir at depth. Those observations describe a volcanic system that remains active. It is not resting forever. It occupies another interval, separating one eruption from the next. Yellowstone illustrates the same principle from a different perspective. Its last major eruption occurred about 640,000 years ago. To most people, such a span feels almost limitless, suggesting permanence and stability. Earth scientists interpret it differently. Yellowstone has experienced three exceptionally large eruptions during roughly 2,100,000 years, together with numerous smaller volcanic events. That history demonstrates an active volcanic system whose intervals are measured across hundreds of thousands of years. Geological time does not treat 640,000 years as an ending, only as part of a continuing sequence. Viewed through that same lens, Taupo's present interval appears neither extraordinary nor reassuring. Approximately 1,800 years have passed since the Hatepe eruption, making this the longest recognized pause following the Oruanui supereruption. Even so, the geological archive contains repeated evidence that volcanic activity resumed after earlier intervals of differing lengths. The rocks preserve continuity rather than finality, recording renewed eruptions without suggesting any permanent conclusion to the system's evolution. Civilizations occupy a much shorter scale. The Western Roman Empire endured for roughly 500 years. The Han Dynasty continued for about 400 years. Most modern nations trace their histories across only a few centuries. These achievements feel enduring within human experience, yet each remains shorter than the average interval separating Taupo's eruptions. Cities rise, governments change, languages evolve, and cultures transform while the volcanic system continues following processes that scarcely acknowledge those transitions. Recognizing this contrast does not invite despair, it offers perspective. Earth existed long before any civilization appeared, and will continue changing long after present societies become part of history themselves. Every generation living beside Lake Taupō has occupied one brief moment within a much older narrative. They built homes, cultivated fields, explored the lake, studied its geology, and entrusted knowledge to those who followed. Geological time neither diminishes those accomplishments nor competes with them. It simply reminds us that humanity and Earth move together across profoundly different clocks, each entirely real within its own measure. Earth preserves its memories in places few people ever see. Deep within Antarctic ice, layers of frozen snowfall accumulate year after year, enclosing tiny traces of distant events that once altered the atmosphere. Among those layers lies the volcanic signal left by the Oruanui supereruption approximately 25,700 years ago. No human witnessed that eruption. No traveler crossed Antarctica to record its effects. Even so, the planet carried evidence from one end of the southern hemisphere to the other and sealed it into the ice. As long as those ancient layers endure, the eruption remains part of a natural archive awaiting careful readers. The same event appears in another language written across the landscape. The Kawakawa tephra settled through the air before becoming part of lake beds, ocean sediments, wetlands, and soils scattered across an enormous region of the South Pacific. It remains one of the most widespread stratigraphic markers in the southern hemisphere, allowing researchers to recognize a single geological moment wherever that distinctive layer appears. A drill core lifted from the seafloor, a sample recovered from an inland basin, or a section exposed along a riverbank can all reveal the same eruption. Earth preserves consistency across remarkable distances, linking separated places through one shared horizon of ash. Yet the geological archive records only certain kinds of truth. Rocks reveal the timing of eruptions, the chemistry of magma, the direction of ash clouds, and the sequence of changing landscapes. They do not preserve the movement of animals escaping advancing pyroclastic flows. They cannot capture the final songs of birds disappearing from devastated forests. They contain no direct memory of the first Polynesian travelers who encountered broad pumice plains and recognized a land shaped by extraordinary forces long before written science offered an explanation. Stone records events with extraordinary precision, while human experience supplies meanings that minerals alone cannot preserve. Seen from this perspective, Taupo becomes more than a remarkable volcano. It offers one of the clearest windows into the ordinary behavior of a living planet. Earth has always accumulated energy, released it, reshaped landscapes, and begun again. Mountains have risen before gradually wearing away. Rivers have found new channels. Lakes have appeared where valleys once existed. Continents themselves have shifted across the globe. Human history occupies only a brief portion of that continuing transformation. Taupo does not create this pattern. It reveals it with uncommon clarity. Nothing within that understanding diminishes the landscape visible today. The lake remains beautiful beneath changing skies. Forested slopes continue meeting the shoreline with graceful contours. Columns of geothermal steam drift upward from selected places around the basin, marking pathways where heat still reaches the surface. Anglers standing in cool water before sunrise, families gathering beside the shore, and travelers crossing the lake all become part of an ongoing relationship between people and place. Knowledge of the geological story enriches those ordinary moments because every familiar scene carries the accumulated work of countless earlier ages. One day, another eruption will leave its own unmistakable signature across Earth. Ash will settle into future sediments, chemical traces will enter ice, and new layers will become reference points for scientists living centuries or millennia beyond the present. They will discover evidence that people once gathered beside this lake, studied its history, crossed its waters, and built communities along its shores. They may also find pale fragments of pumice still arriving upon distant beaches, continuing a journey that began long before any living memory and never truly came to an end. Knowledge grows through patient observation. Every earthquake recorded, every subtle rise or fall of the ground, every sample collected from geothermal waters becomes another sentence in a conversation between scientists and the volcanic system they study. Around Lake Taupō, that conversation has become more detailed than at any other point in history. Each year adds measurements unavailable to previous generations, gradually transforming isolated observations into a continuous portrait of a living caldera. The monitoring network surrounding Taupo ranks among the most advanced ever established for a rhyolite volcanic system. Sensitive seismic instruments detect earthquakes too small for people to notice. Global navigation satellite system stations measure gradual movements of the ground with remarkable precision. Satellite radar repeatedly maps surface deformation from orbit, revealing patterns that would otherwise remain invisible across the landscape. Researchers also monitor geothermal chemistry, tracking changes in fluids rising from depth, while underwater instruments near Horomatangi Reef contribute information from the lake itself. Together, these independent observations provide multiple perspectives on the same evolving system, allowing each dataset to strengthen the interpretation of the others. The value of these measurements increases steadily with time. Following improvements made after the unrest of 2019, the expanded seismic network began collecting a richer baseline describing ordinary behavior beneath the caldera. Every additional month and year helps distinguish familiar patterns from changes that deserve closer attention. A volcano rarely behaves in exactly the same manner from one decade to the next, making long records especially valuable. The growing archive allows scientists to compare present activity with earlier observations while reducing uncertainty about natural background variation. One of the most common questions concerns warning time before an eruption. The honest answer remains dependent upon the scale and character of the event itself. A relatively small eruption could develop over hours or several days if magma rises rapidly toward the surface. A larger eruption, accompanied by clearer unrest, might provide warning extending across weeks or even months. An event approaching supereruption scale could generate detectable changes years beforehand. Although present science cannot guarantee such a sequence, geological history shows considerable variety, and researchers continue refining models that connect monitoring data with volcanic behavior. Preparation, therefore, extends beyond scientific instruments alone. New Zealand maintains emergency planning for the Taupo region, including volcanic alert levels, communication procedures, and evacuation routes designed to guide communities if volcanic unrest intensifies. These plans are reviewed and updated as research improves understanding of the caldera. No living generation has experienced a major Taupo eruption, yet planning continues because geological history demonstrates that long intervals eventually conclude. Preparation reflects informed stewardship rather than certainty about timing. Perhaps the greatest gift modern science offers is understanding itself. The civilizations connected with earlier eruptions possessed observation, resilience, and cultural memory, though they lacked the geological framework available today. Decades of fieldwork, laboratory analysis, drilling, dating techniques, and continuous monitoring have revealed how Taupo evolved across approximately 300,000 years. That knowledge carries responsibility. Information gains its greatest value when it informs decisions made long before they become urgently necessary. The next volcanic layer, deposited by Taupo, will eventually settle into lakes, soils, ocean sediments, and other natural archives. Future researchers will recognize it, just as present scientists identify older eruptions preserved within Earth's record. Whether that layer also reflects a society strengthened by foresight depends upon choices made during the long interval before it arrives. Careful attention, sustained across generations, becomes another form of preparation, one measured not in days or decades alone, but in the enduring partnership between scientific understanding and the landscape that inspired it. Recognition rarely follows geological importance. It follows stories repeated often enough to become familiar, photographs shown often enough to become iconic, and names spoken until they settle into public memory. Taupo has never followed that path. It remains one of the most active rhyolite supervolcanoes on Earth, the location of the planet's most recent known supereruption, and the source of the most violent eruption of the past 5,000 years. Outside New Zealand and the comparatively small community of volcanologists who study such systems, its name is still unfamiliar to many people. Attention has its own patterns, shaped less by geology than by culture. A place featured in books, documentaries, classrooms, and news reports gradually becomes part of the world's shared imagination. Each new mention reinforces the last, making future attention even more likely. Another place of equal scientific importance may remain at the edge of awareness simply because the cycle never fully begins. Public knowledge grows through repetition, and repetition often follows visibility more readily than significance. Volcanic systems do not arrange themselves according to reputation. They continue evolving regardless of how often they appear on television screens or in popular conversations. Topo is not diminished by receiving less international attention than Yellowstone. The difference lies in familiarity, not geological importance. Confusing those two ideas can shape how societies understand natural hazards, where research receives public interest and which landscapes become widely recognized beyond the scientific community. History offers an illuminating comparison. During the 3rd century after the Common Era, observers in distant civilizations recorded unusual changes in the atmosphere without knowing that a great eruption had occurred across the Pacific Ocean. They documented what they could see, while the true source remained beyond their understanding. The modern world possesses satellites, seismic networks, laboratories, and international scientific collaboration, yet many people still picture global volcanic risk without including Taupo at all. The absence exists within public awareness, not within the geological record, which has preserved the volcano's history with remarkable consistency. That contrast creates an unusual irony. A volcanic system capable of producing eruptions that reshaped landscapes, altered distant skies, and left markers spread across the southern hemisphere is also home to one of the world's admired freshwater lakes. Visitors arrive to fish for trout, paddle across open water, explore geothermal areas, or spend time along the shoreline. More than 1,300,000 people visit the region each year, experiencing a landscape celebrated for recreation, scenery, and outdoor life. Those experiences are entirely genuine, existing alongside the deeper geological processes that continue far below the surface. Knowledge does not diminish beauty, it broadens it. Understanding how Lake Taupō formed, how its surrounding valleys evolved, and how researchers continue watching the volcanic system adds another dimension to every view across the water. Familiarity replaces uncertainty with context. Scientific observation, historical evidence, and careful monitoring together provide a clearer picture of the landscape than reputation alone ever could. Perhaps that is the quietest purpose of this story. It has never been an invitation to imagine catastrophe above all else. It has been an invitation to notice a place whose significance has long exceeded its fame. The evidence has been gathered through decades of research. The instruments continue recording. The geological archive remains open for anyone willing to read it. Only attention has lagged behind. Once attention arrives, understanding has somewhere to begin, and Lake Taupo can be known for the fullness of its story, as well as the beauty reflected upon its waters. Morning arrives over Lake Taupo without announcing the history resting below its surface. Light spreads across approximately 238 square miles of water. The surrounding mountains appear as shifting reflections that change with the angle of the sun. Along parts of the shoreline, geothermal steam rises where heat still finds pathways upward. Trout pass through deeper water while warmer currents drift upward from hydrothermal vents near Horomatangi Reef. Every familiar scene belongs completely to the present, even as it rests upon a landscape shaped across spans of time that reach far beyond memory. Far below the lake, between roughly 4 and 5 miles beneath the surface, molten rock remains where it has persisted through repeated cycles of volcanic activity. Temperatures within portions of that magma are estimated to range between approximately 1,380 and 1,650 degrees Fahrenheit. Dissolved gases remain held under immense pressure. Research completed during 2019 and observations reported during 2022 confirmed that fresh magma continues entering the system, while sections of the caldera continue rising and falling in response to changing conditions. The reservoir has endured for approximately 300,000 years. It has not cooled into permanence. It continues evolving according to the same physical laws that shaped every earlier eruption preserved within the geological record. Life continues above that reservoir with ordinary rhythms. Someone launches a kayak into the water before the day grows warmer. Someone pauses along the waterfront in the town of Taupō while deciding where to share a meal with family or friends. Another traveler follows the northern shoreline with open windows, welcoming the summer air as the lake stretches beside the road. Children skip stones across the water. Anglers wait with practiced patience. None of these moments conflict with the geology surrounding them. They exist together, each entirely real, each belonging to the same landscape. Earth itself asks for no recognition before continuing its work. Magma does not wait until researchers finish mapping underground reservoirs. Pressure does not pause while scientific papers are written or published. Chemical reactions proceed without regard for human calendars, governments, or generations. Long before life emerged, the planet followed these same principles, and they remain unchanged today. Observation expands understanding, though it does not alter the underlying processes that sustain volcanic systems. There is, however, something remarkable in humanity's ability to recognize what this place truly is. Through centuries of careful study, scientists learned to read buried forests, volcanic ash, lake sediments, crystals, earthquake patterns, and Antarctic ice. Each discovery added another piece to a story written by Earth itself. That accumulated knowledge cannot prevent every future eruption, yet it offers the clearest picture any generation has ever possessed. It allows preparation to replace uncertainty where evidence can guide it, and encourages decisions grounded in observation instead of guesswork. One final truth remains. The annual probability of a major Taupō eruption is less than 0.1%. Geological evidence, gathered across approximately 300,000 years, also indicates that the volcano will erupt again. These statements do not contradict one another. They describe different scales of the same reality. The interval continues. The lake continues, reflecting the sky. Instruments continue recording. Deep below, the volcanic system remains alive, while above it, people continue living, learning, and adding their own brief chapter to a story that Earth has been writing for far longer than memory can reach. One day, on a timetable that no calendar can provide, Lake Taupō will add another chapter to its volcanic history. Whether that future eruption is modest or immense remains unknown. Its ash, however, will begin a familiar journey. Fine particles lifted high into the atmosphere will travel with prevailing winds, crossing oceans and continents before settling upon distant landscapes. Some of that material will eventually fall across Antarctica, where snowfall will bury it layer by layer. Compression will transform those annual accumulations into ice, preserving the volcanic signature within a frozen archive that extends across ages. That future layer will contain far more than ordinary dust. Embedded within the ash will be the distinctive chemistry of Taupō's magma, including its unusually high silica content, trace elements, and sulfur isotopic composition. Scientists equipped with instruments beyond those available today will examine microscopic fragments and reconstruct the eruption with remarkable precision. What begins as drifting volcanic particles will become a permanent geological reference, allowing future researchers to identify the source, establish an exact age, and compare it with every earlier eruption already preserved within the same frozen record. The story will not exist only in polar ice. Fine sediment settling onto the floor of Lake Taupō at this very moment is already creating another archive. Grain after grain accumulates across the basin, preserving pollen, minerals, microscopic organisms, and chemical signals from the surrounding environment. The volcanic unrest observed during 2022 will remain detectable within those deposits through subtle physical and chemical changes. Equally important, those layers will show that no eruption followed during that particular episode. Future sediment cores will preserve the interval itself, recording a period of observation, movement, and continued waiting. Those who eventually study the next volcanic layer have not yet been born. Their coastlines may differ from those of today. Their climates may have shifted. Languages familiar now may have changed beyond recognition, while new civilizations build their own understanding of the planet. When they recover an Antarctic ice core or drill through sediments collected from the lake floor, they will encounter a sequence already stretching far into the past. They will recognize the immense Oruanui supereruption, the succession of later eruptions that followed, the long interval preserved after Hatepe, and then another unmistakable volcanic horizon announcing that the interval had finally reached its conclusion. The geological record will answer many questions with extraordinary confidence. It will identify the chemistry of the magma, the timing of deposition, and the reach of volcanic ash carried through the atmosphere. Other questions will remain beyond the reach of minerals and ice. Those future researchers may wonder how people experienced the years before the eruption. They may ask whether communities gathered beside the lake, whether visitors crossed its waters, whether scientists understood the volcanic system beneath them, and whether careful monitoring provided all the warning that circumstances allowed. Rocks and ice will preserve evidence of physical events. The texture of ordinary human life will exist only through whatever records people choose to leave behind. Already, the Kawakawa tephra from approximately 25,700 years ago rests within Antarctic ice, while deposits from the Hatepe eruption remain preserved in sediments awaiting every new investigation. Another layer will someday join them. Earth continues assembling its archive without interruption, adding page after page through ordinary geological processes. Every eruption becomes part of that enduring record, and every interval, including the one unfolding now, occupies its own place within the same unbroken story. History often remembers the events that receive the greatest attention, while the planet follows a different measure entirely. Geological forces neither seek recognition nor depend upon human awareness. They continue shaping continents, raising mountains, opening valleys, and feeding volcanic systems across spans of time far exceeding civilizations. Many of the most consequential processes unfold far from headlines, beneath familiar landscapes, or across intervals so long that memory alone cannot preserve them. Their importance exists independently of whether they are widely known. Taupō stands among those places. It is a supervolcano and the most frequently active rhyolite caldera on Earth. Approximately 25,700 years ago, it produced the planet's most recent known supereruption. During the 3rd century after the Common Era, its Hatepe eruption became the most violent volcanic event of the past 5,000 years. Today it lies beneath a celebrated lake in New Zealand, where research confirms that an active magma system remains several miles below the surface. Measurements continue showing that portions of the caldera rise and fall as magma and volcanic fluids move within the crust. Since the Oruanui supereruption, approximately 28 eruptions have occurred, while the present interval of roughly 1,800 years has become the longest pause in that entire post-Oruanui sequence. Across this journey, the lake has revealed itself through many different records. Buried forests preserved moments of destruction. Layers of volcanic ash connected distant landscapes. Sediments accumulated without interruption. Antarctic ice carried chemical traces across the southern hemisphere. Earthquakes, ground movement, geothermal waters, and laboratory analyses combine to describe a volcanic system still changing today. Piece by piece, centuries of scientific work transformed scattered observations into a coherent understanding of one remarkable place. Knowledge does not alter the physics governing magma, yet it changes the way the landscape is understood. A name once unfamiliar becomes part of a broader map of Earth's geological activity. The shoreline is no longer only a destination for travel, recreation, or fishing. It also becomes the visible expression of processes operating far below human sight. Understanding replaces absence. Awareness grows through evidence gathered patiently across generations, allowing the planet to be seen with greater accuracy than before. That habit of careful attention reaches beyond Taupo itself. Around the world, other volcanic systems continue evolving with histories that remain unfamiliar outside scientific circles. Some are closely monitored, while others still hold unanswered questions. Their significance does not depend upon popularity or the frequency with which they appear in public conversation. Geological reality remains constant whether many people recognize it or only a few. Accuracy begins by allowing evidence, rather than reputation, to shape understanding. Even now, ordinary moments continue around Lake Taupō. Water reflects the surrounding mountains as changing light passes across the surface. Geothermal steam rises along parts of the western shoreline. Boats cross the lake. Families gather near the water's edge. Visitors pause to admire a landscape formed through countless earlier chapters of Earth's history. Every one of those moments belongs naturally to the place exactly as it exists today. Far below that water, between approximately 4 and 5 miles beneath the lake, molten rock remains within the volcanic system that has endured for approximately 300,000 years. It continues receiving new material from deeper within Earth. It continues changing, one movement at a time. Its story has not reached its final page.